Merhabalar tekrardan. İsterseniz yavaştan başlayalım. Ee, Başlamadan önce ufak bir giriş yapacağım Türkçe olarak. Daha sonra sözü sunucumuza devredeceğim. Öncelikle hepiniz hoş geldiniz. İsmim Ali Fırat Bucak. BİAS'ta Titreşim-Akustik takım lideri olarak çalışıyorum. Görevim titreşim-akustik sensörlerinin ve ekipmanlarının satış ve desteği. Yaklaşık 6 yıldır BİAS'ta çalışıyorum. BİAS olarak test-ölçüm, test hizmetleri, analiz, Ar-Ge gibi konularda mühendislik hizmetleri veren bir firmayız. E, Test ölçüm bölümünden bahsedecek olursam bu alanda mesleklerimiz yani yurt dışından bazı partnerlerimizin ürünlerinin Türkiye'de temsilciliğini gerçekleştiriyoruz. Aynı zamanda satış ve saha hizmetlerimiz de bulunmakta. Bununla birlikte Dytran da bu partnerlerimizden bir tanesi. Dytran bizim uzun yıllardır çalıştığımız özellikle piezoelektrik sensörler konusunda hizmet veren alanında yine dünyada öncü bir firmalardan bir tanesi. Dytran'la çalışmayı seviyoruz. Uzun zamandır birlikte güzel işler yapıyoruz. Türkiye'de ve dünyada birçok kullanıcısı, e, ürünlerin birçok kullanıcısı olan bir firma. Alanları ise piezoelektrik sensörler. Piezoelektrik sensörlerinde kuvvet sensörleri, basınç sensörleri ve ivme ölçerler genel olarak üretimini gerçekleştiriyorlar. Bizim bugünkü ana odak noktamız titreşim konusu olacak. Biraz da piezoelektrik ivme ölçerlerden yoğunlukla bahsedeceğiz. Webinarımıza gelecek olursak içeriğimiz şu şekilde. Piezoelektrik sensörleri bir giriş yapacağız. Bunların ne olduklarından, ne amaçla üretildiklerinden, bu sensörlerin karakteristiklerinden, seçim kriterlerinden ve daha sonra ise bazı uygulama tüyolarından bahsedeceğiz. Webinarımız yaklaşık olarak bir saat sürecek. Webinar esnasında aklınıza takılan sorular olursa chat kısmına veya question and answer kısmı var yukarıda. Oraya yazabilirsiniz. Webinar sonunda bunların hepsini tek tek cevaplamaya çalışacağız. Şimdi izninizle İngilizce geçip sunucumuzu tanıtacağım ve daha sonra webinarımıza başlayacağız. Hello everyone, thanks for attending our webinar. And I would like to introduce our presenter, Kevin Mestora. Kevin is sales director at Dytran, and he has about 30 years of experience in this area. Kevin, thanks for being here, and you can start introducing yourself and your presentation.
Thank you, Ali. I appreciate it. And thank you for BIAS for inviting us for this presentation. We're excited to be here. Thanks, everybody, for attending. I'm going to go ahead and share my screen. And Ali, can you see it okay?
Yeah, I can see it.
Fantastic. I'm going to go ahead and launch the presentation. So just introductions very quickly. I'm Kevin Westora, as he said, with Dytran Instruments. I've been with the company 20 years. It's a great company to work for. It's a very exciting market that we get to serve with many exciting customers from aerospace to space to automotive and oil and gas, many others. So I love working for the company. I've been in the sensor industry, as he said, for many years. Prior to this, I was in the strain gauge industry. And now for 20 years, I've been in the piezoelectric sensor industry. In my presentation today, I will talk a little bit about both piezoelectric technology as well as variable capacitance MEMS DC accelerometer technology. We do offer both at Dytran. And so I'll kind of discuss the pros and cons of the two different technologies that you can use for measuring shock and vibration. These are the topics that we're going to go over today in the presentation. I'll try and keep us on track here and on time. I'm not going to go through this list. I'm just going to jump right into the presentation. Just a little bit about Dytran. We were founded, as I mentioned, in 1980, about 45 years ago. We are located in Los Angeles, California. We do love making custom solutions. So if there's a customer that has a requirement that we have not developed a sensor for already, then we're happy to make a new sensor. We make about 30 to 50 new sensors or cables every year. And we like to be very innovative, whether it means ultra low temperature, ultra high temperature, whether it's low noise, whether it's a DC MEMS technology, or even 6 degree of freedom. We love to be innovative. For accreditation, Dytran has AS 9100 for aerospace. Space and aerospace make up probably 70% of our business. So whether it's on airplanes or helicopters or rockets, that's a big part of our business. And then we're also 17025 ISO accredited from A to LA. So that means every accelerometer that we ship comes with an accredited calibration certificate. Okay, that's a little bit of our history. Some of the capability that we have at Dytran. We have a very broad product line. We do pressure, force, we do vibration recorders, we do charge mode and IEPE accelerometers. We have significant in-house engineering resources. We're a very technical company. Cables are very important, a very important part of what we offer at Dytran. We're one of the few accelerometer companies that still make cables at our factory. We ship 7,000 cables every month, so it's a very important part of what we do. We have a very extensive CNC machine shop that we run 24 hours a day, 5 days a week. I think we produce 40,000 machine parts per month to manufacture accelerometers. And I truly believe we have a world-class sales support team with our team there, BİAS in Turkey. We have sales partners in every major country, as well as our factory supporting any questions or inquiries that you might have. Okay. Okay, so let's jump into the presentation. I'm here to talk about piezoelectric technology. So a little bit of the history of Dytran. I'll make a very long story short. Our founder, Nick Chain, started Dytran in 1980, but before that, he founded a company called PCB in 1968. And before that, he was working at a company called Kistler in 1958. So it's a very, very long history that Dytran has had in this industry. It's a technology that goes back to the 1940s and 50s with B&K and Kistler. And yet, even though this technology has been around now for over 100 years, we still continue to make amazing sensors and new sensors with this technology. And the reason that we can make, 30 or 50 new products every year, even though we've been making sensors in this industry for, almost 100 years, is because of these reasons here. With piezoelectric technology, we can offer a small sensor. We literally make the world's smallest accelerometer, IEPE accelerometer, 0.2 grams. So lightweight. We can make sensors that are a two-wire operation. We're going to talk quite a bit about that in the presentation today. What is IEPE or ICP, if you're familiar with that? We can make sensors with a wide dynamic range. So with piezoelectric technology, we can make sensors all the way down to fractions of a G, 0.5 Gs, 0.1 Gs for seismic applications. And then we make sensors that are 100,000 Gs with this technology. So quite the wide variety of dynamic ranges. Temperature range is even more amazing for me. We make sensors that are rated to minus 320 Fahrenheit, all the way up to 650 C rated accelerometers. So the same piezoelectric technology can go from minus 250 C to plus 650 C, which is amazing. So from cryogenic applications in space to turbine engine applications with high temperature. These sensors are ultra low noise. As I mentioned, we also offer DC MEMS accelerometers for vibration monitoring. The DC MEMS accelerometers, we offer the lowest noise DC sensors in the world. However, if you look at a piezoelectric accelerometer compared to a DC MEMS accelerometer on an O-scope, you would exponentially see a difference in noise with piezoelectric. They are very, very low noise. When I started at Dytran, I was very surprised that probably 70% of all the sensors that we sell are 10 millivolt per G, 500G sensors. And really, there's not that many applications that have 500 Gs of energy in the world. But the reason that we sell so many 10 millivolt 500G sensors is because you can resolve milli-Gs with a 500G accelerometer. So even if your application is 50 Gs, you can use a 500G accelerometer and get very good data with that sensor. So you could use the same sensor for multiple applications, multiple tests. And that's a big reason for it. That's not the case with DC MEMS accelerometers. If I had a 10G application for a DC MEMS accelerometer, I cannot use a 200G sensor because my noise signal to noise ratio would not give me good data at 10 Gs. All right. The other reason that we use piezoelectric sensors is simple signal conditioning. I apologize, I don't remember what data acquisition system BİAS offers, but I'm sure they have a world-class data acquisition system.
Yeah,
Today,
Siemens.
Siemens, that's right, you
Yeah,
guys
we
just changed,
actually
right?
start working with Siemens, and we have some other options for customers. Yeah.
Yeah, Siemens is obviously world famous, and now every data acquisition company in the world offers IEPE, ICP cards, channels for their data acquisition. So it's very easy to use these accelerometers. That was not the case 20 years ago. You had to use external IEPE conditioning to condition and power the sensors. But today, everybody has and offers IEPE, especially Siemens on their LMS hardware. And then lastly, we have broad frequency range. So we make sensors, like I mentioned, for seismic applications that go down to fractions of a hertz, 0.1, 0.05 hertz. And then we have sensors that go all the way up to 20 kilohertz. So a very broad frequency range. That's not the case with the DC MEMS accelerometers. They go from 0 hertz, hence the word DC frequency, to roughly about 1 or 2 kilohertz maximum. So they're very limited in the upper frequency. But piezoelectric sensors typically can easily go to 10 kilohertz. As far as where we use piezoelectric accelerometers, as far as the Dytran customer base, as I mentioned before, most of our customers are in the aerospace, space, the military applications. We do a lot of automotive. We do some oil and gas, energy monitoring, some civil structure and seismic monitoring. But for the most part, the biggest thing that we offer, the biggest application we get involved with at Dytran would be shakers. So on a day-to-day basis, I spend most of my time on an electrodynamic shaker testing customer product. So the customer either uses their own shakers or they use an outside independent lab for testings. But that's mostly where I spend my time is on shakers. All right, the next thing I want to talk about is how to select a proper accelerometer, how to select a proper sensor. The first thing that we ever talk about and look at is the size and the mass of the product that you're testing. Because the last thing we ever want to do is, if your test article is 3 grams, is to select an accelerometer that weighs 10 grams to measure the vibration of that test article, because you're going to mass load the test article. You're going to change the frequencies, the dynamics of the test, and not get good data. So the first thing we ever look for is what is the space and mounting and the maximum mass that the test article can accommodate. Most of my customers, 99% of my customers, come to me and want smaller accelerometers. They want smaller, smaller, smaller. Very, very rare, only a few times in my 20 years has anybody ever asked for a larger sensor. Everybody wants ultra miniature. The next thing that we talk about is the vibration level. What is the energy that we're going to be measuring? What G range that we need to measure? If you don't know what it is, then if you could share some rough details of the application, either myself or our engineering team can determine roughly what the appropriate G level would be for your application. And then the next thing we need to do is talk about frequency, both minimum frequency and maximum frequency. What's the lower end frequency that you need to measure and the upper level frequency that needs to be measured? Then we get into the environment. What is the temperature that this sensor is going to be exposed to and for how long? What's the duration? As I mentioned, we can go minus 320 Fahrenheit all the way up to 1200 F Fahrenheit. So we have sensors that can go quite dynamic range in temperature, but the temperature range will determine quite a bit which sensor technology that we utilize. And then in that environment, are they going to be exposed to any corrosive elements? I was just on an email string yesterday where the customer wanted to submerge the accelerometer in gasoline. And so engineering had some very specific instructions on what not to do, what to do when you're submersing an accelerometer in gasoline. You know, there's a lot of things that you have to take into account, like the adhesive that you're going to be using, things like that. So we need to know that. And then physical clearance, kind of like the mass situation is, you know, is there any physical clearance situation? Do you need the cable to go up, the cable to go sideways, things like that. And then, of course, what kind of cable? What's the length, et cetera. The cable is very, very important. So I'll talk quite a bit today about cables. In most sensors that you might utilize, whether it's a strain gauge or a load cell or a torque sensor or a flow meter or a pressure sensor, the cable is a necessary, you know, part of the process to plug the sensor into the data acquisition system. But in accelerometers, the cable is a part of the test. It shakes and vibrates along with the accelerometer. So cables are a very, very important part of what we do at Dytran, a very important part of the solution that you need for measuring vibration. I have an entire presentation like this one, just specifically on cables that I'd be happy to send if anybody is interested in it. I also have an email, not a presentation, but an email. At Dytran, we're very fortunate to have a PhD material scientist on staff, and he has put together an email with suggested adhesives for various applications based on if it's a low temperature application, high temperature, if it's going to be a quick test or a long duration test. So I have a whole list of different adhesives. If you're interested in that, I could send that out as an email. Okay. All right, the next thing I want to talk about a little bit is the difference between dynamic measurements and static measurements. In this presentation, I usually use the crossover point of 500 hertz. So below 500 hertz is a static measurement, and above 500 hertz is a dynamic measurement. That's actually changing quite a bit. The DC MEMS accelerometers, variable capacitance technology, is getting better. We now offer a DC MEMS accelerometer that actually measures out to 7 kilohertz, which is quite amazing. But for this discussion, we'll just use for now 500 hertz. So a dynamic event means that the physical quantity that you're trying to measure, whether it's acceleration, pressure, force, whatever it is rapidly changing over time, i.e. over 500 hertz. Examples of those would be electrodynamic shakers, NVH testing, any kind of transmission or engine testing, turbo pump testing. That would all be dynamic events, and that would usually mean that I'm going to use a piezoelectric accelerometer for that application. The static measurement, same thing, the physical quantity that we're trying to change changes slowly over time, i.e. sub 500 hertz, or even down to DC, 0 hertz frequency. Examples of that would be the constant acceleration to gravity, and as well as, let's say, your bathroom scale. Bathroom scale is a great example of a static measurement where you stand on it, it's very static, and it gives you your mass or your weight. I'll get back to that here in a minute. So static measurements we would typically use, you could use a piezoelectric sensor, but you would typically use a DC MEMS accelerometer if you need 0 hertz. If your static measurement is, say, 20 hertz, you could probably use either sensor. So one of the examples I always give is, let's say you have an application that is 100 hertz at room temperature at 100 Gs. Size doesn't matter. The temperature is room temperature. Which sensor would you choose? Would you choose a DC MEMS accelerometer, or would you choose a piezoelectric accelerometer? And the answer is either sensor would work. We have sensors, DC MEMS sensors, that are perfect for that application, and we have piezoelectric sensors that are perfect for that application. What usually dictates the sensor that you choose is one of a couple things. One, the legacy of that test. Maybe the industry or the customer is always accustomed or used to seeing data from one variable, one technology or another, and they want to stick with that technology for repeatability. That would usually drive what sensor you might use. The other thing would be your data acquisition system. So if your system is set up for IEPE sensors, you don't want to pick a MEMS sensor because you'd have to power it externally. But conversely, if your system is set up for DC power, you would probably better off picking a DC MEMS accelerometer and using a simple 10-volt DC power versus trying to power IEPE externally or getting another card for your data acquisition system. So that's usually what dictates the type of sensor. I would say, though, in my humble opinion, you would never ever use a DC MEMS accelerometer unless you need 0 hertz frequency. If you don't need 0 hertz, and many customers do, if you're in the aerospace industry or if you're in automotive, many applications require 0 hertz frequency. So then you must use a DC MEMS accelerometer. But if you don't need that, then I would always use a piezoelectric sensor because they're cheaper and they're smaller in size. Okay. All right, I want to go back to the bathroom scale because the bathroom scale is a perfect example of a transducer. And so at Dytran, we make sensors. We call them accelerometers, but we also call them transducers. A transducer is the ability to take one form of energy and convert it into another form of energy. So your bathroom scale takes your mass, your weight, converts it into a digital readout. We take acceleration, pressure, or force, and we convert it into an electrical readout. So that's what we make at Dytran. We make a transducer. So I've been talking quite a bit about a DC MEMS accelerometer. Let me see if I have a picture of one here real quick, and then I'll come back. Here, nope, there's no picture of a DC MEMS accelerometer here. Well, that's too bad. All right, never mind. Not at all. Not one. All right, never mind. Sorry, I'll put one in here for a future reference. Let me just make sure I'm not looking at one and I don't see it. No. So I don't have a DC MEMS accelerometer picture. But this is the technology of a variable capacitance DC MEMS accelerometer. So there are 3 ways to measure acceleration in the industry. You can measure acceleration with piezoelectric technology, which is what we're talking about today. You can use a piezo-resistive technology, which is a strain gauge based technology. And that technology is used for 2 applications, one for shock, high shock, and one for crash testing in automotive. Those 2 applications use piezoresistive because it's a high G application. The third way is variable capacitance DC MEMS accelerometers. And all of the accelerometer companies offer this technology: Dytran, PCB, Kistler, and Devco. We all offer these sensors. And so this is what you're looking at. This is the technology. It's a MEMS chip that resides as the technology. And if you look at this lower picture, you have a lower substrate, which is a lower capacitive plate, and then an upper capacitive plate separated by this pedestal. And so this upper plate is free to move. It actually rotates around that pedestal. And then we gas damp that space in between so that it's not free to just vibrate uncontrollably. We dampen it with a nitrogen gas. And as that plate moves compared to the lower plate, it changes the capacitance between the two plates. And it's extremely linear, that change in capacitance. So as you rotate the accelerometer or you shake up and down the accelerometer, it changes that capacitance. So that's why these are limited. These can measure DC frequency because as you're sitting still, it'll measure that capacitance, but then it's limited in how many Gs you can measure. The maximum Gs that we offer at Dytran right now is 400 Gs for this application, for this technology. So anyway, that's a little bit of overview of the capability and technology of a DC MEMS accelerometer. So let's get back to the piezoelectric sensors that we're here to talk about. So now that we know what a transducer is, what is a piezoelectric transducer? So piezoelectricity is the ability of some material like a crystal or a ceramic to generate an electrical potential in response to an applied mechanical stress. It comes from the Greek word piezo, which means to change or to squeeze or to press. And basically, let me see, let me get a picture of it here. I think I have a picture of a crystal, maybe. There it is. So right here is this crystal right here on the left side. You can see this stack of crystal. It's just a rock. I call it a rock. As we squeeze that rock, we squeeze that crystal, you get an electrical output. And that electrical output is measured in coulombs. And the amount of coulombs that we get out is in the picocoulombs. And pico is very small. I believe it's 10 to the negative 12 in size. So it's a very, very, very small output, very small charge output that we get by squeezing this crystal. So I like to say that it means that we're changing the electricity. Piezo means we're changing the crystal, just like piezo resistive means that we're changing the resistance of a strain gauge. So a strain gauge, if you strain gauge a beam and you excite it with 5 volts, and then you strain that beam, you bend the beam, you're straining the wire, which changes the resistance in the wire, and that change in resistance is extremely linear, so you can then equate that change in resistance, the change in the deflection of the beam, to a force. That's kind of what we're doing here with piezoelectric, but instead of strain gauging a beam, we're squeezing a crystal. And the crystal is like a sponge. If you squeeze it a little bit, you get a little output. If you squeeze it a lot, you get a lot of output. And it's very linear. Sensor companies love linear material, like strain gauges and like piezoelectric material. All right. There are many types of piezoelectric material in the industry. Dytran uses, for the most part, quartz and ceramic. Those are probably 90% of what we use. And then for ultra high temperature, anything over 250 C, we use very special piezoelectric material like lithium niobate or langatate or tourmaline. We don't actually use tourmaline. And Devco uses tourmaline. A company we just bought in Austria called the Piezocryst uses GaPO4 called gallium orthophosphate. a very nice, amazing material for high temperature. But for the most part, we use quartz and ceramic, PZT ceramic. And the difference between quartz and ceramic would be quartz is used for, let's say, high temperature over 100 C, and it's used for high Gs, so 500 Gs or higher. Ceramic is used for modal analysis, so it's low frequency, low G, under 500 Gs typically, and very low temperature, under 100 C, and very low noise. So quartz is used for like engine testing, transmission testing, brake testing, turbo testing, and ceramic is used for modal analysis, where you need very low frequency, very low noise, and high output. That's would be the difference. All right, now that we know what a piezoelectric transducer is, let's talk about the two different types of sensors. So a piezoelectric charge mode accelerometer means that there's no amplifier in the sensor. I'm going to go forward here and look at the sensor right here. So on the left here is a piezoelectric charge mode accelerometer. So there's no amplifier at all. There's just a stack of crystals. And if I shake this accelerometer with no voltage, no power supply, I get an output. All right. It's called self-generating. I shake the accelerometer and I get an output. The problem is, as I mentioned, it's a picocoulomb output, and not very many data acquisition systems can read picocoulombs. So we have to convert that picocoulomb signal to a voltage. So let's go back here. And so a charge mode has no amplifier. It's a picocoulomb per G output. At some point, we need to amplify the signal. We either amplify that signal in an inline charge amplifier, or we use the data acquisition system charge amplifier, like the Siemens system comes with a charge amplifier option, and you can use that. Otherwise, we put an amplifier inside the accelerometer, and we call that a voltage mode accelerometer. And now you get a millivolt per G output. You get 5 volts at full scale. So if you have a 500 G accelerometer, you get 5 volts at 5 Gs. If you have a 100 G sensor, you get 5 volts at 100 Gs. Okay. In my opinion, you would never use ever a charge mode accelerometer except for one reason, and that would be the temperature limitation of the amplifier in the voltage mode accelerometer. So the voltage mode amplifier is limited to roughly around 160 C. Once you get above 160 C, we need to take the amplifier out of the accelerometer and put it somewhere else. Okay. The amplifier has a name. It's a very strange, the accelerometer industry is a very strange industry, in my opinion. Every accelerometer company has a different name for that amplifier. Some people call it IEPE. Some people call it ICP. Some people call it CCLD. Some people call it isotron, piezotron, LIVM. So literally every accelerometer company has a different name for that amplifier, but they all mean the exact same thing. An IEPE accelerometer is a drop-in replacement for any ICP PCB accelerometer. They're literally the exact same thing. And we're going to show you the schematic here in a minute of what I'm talking about. That is not the case with DC MEMS accelerometers. With DC MEMS accelerometers, every accelerometer is different from any other accelerometer. Any Dytran MEMS accelerometer is different than other Dytran sensors, let alone a Dytran sensor compared to a Kistler accelerometer. So in the DC world, every sensor is different. You need to pay attention to the power supply, the current draw, whether it's single-ended or differential, what the power supply is, etc. So that's not the case, though, with IEPE. Every IEPE accelerometer from any manufacturer is a drop-in replacement to the other one. Okay, exactly the same, which is unique. All right, now that we know what a voltage mode accelerometer is, let's talk about what some of the fundamentals of them. So with a voltage mode sensor, an IEPE or an ICP accelerometer, I can use many different materials. With a charge mode accelerometer, I'm limited in what material I can use because it's typically high temperature. I cannot use ceramic, for example, in a charge mode accelerometer. But in a voltage mode accelerometer, I can use any crystal. So I can use quartz, I can use ceramic, I can use other bismuth titanate. It has the electronics built in. It's stable over a pretty broad range. Typically, we quote our voltage mode sensors are from -40 to 165C, so pretty broad. We do have some sensors that will go -250C IEPE, which is pretty amazing. I do now have a new sensor that will go to 200C IEPE. So we keep extending this temperature range that IEPE sensors can utilize. As I mentioned earlier, almost every data acquisition system comes with an IEPE power option or ICP. And we can utilize TEDS in an IEPE accelerometer. I won't spend a lot of time on TEDS, but TED stands for Transducer Electronic Data Sheet. It means that I put the calibration certificate of the accelerometer inside the sensor so that when you plug it into your Siemens LMS system, it automatically calibrates. That's what TEDS means. And we can put TEDS in any voltage mode accelerometer. All right, let's talk a little bit about IEPE, ICP, isotron, piezotron, CCLD, whatever you guys want to call it. They all mean the same thing, and this is what it means. It means that they have a voltage input. It's 18 to 24 volts DC, and it's 2 to 20 milliamp constant current. That's the key. So two things here that are very important to take away. IEP accelerometers are constant current, 2 to 20 milliamp. Yes, there's a voltage associated, but the important part is it's constant current. Typically, the data acquisition system gives the sensor 4 milliamps, which is very adequate to power the sensor. The only time you would want more than 4 milliamps would be if you're running a very long cable to the sensor, let's say 100 meters. If you're doing a 100-meter cable, you would want to boost that up to 20 milliamps. Other than that, 4 milliamps is very adequate. The output is proportional to the acceleration. Like I mentioned, you get plus minus 5 volts at full scale G range for every IEPE accelerometer. And this is a very, very unique system. It's a 2-wire system, so you have signal on one wire and then power and ground on the same other wire. So you can use for a single axis accelerometer, it's a coaxial cable, and for a triax, it's a 4-wire cable. For DC MEMS accelerometers, that's not the case. On a DC MEMS accelerometer, you would need 4 wires for a single axis, plus minus in, plus minus out, and you would need 12 wires for a triax. So the cable is much easier to deal with on an IEPE accelerometer versus a DC MEMS accelerometer. And then this last part here is related to this 18 to 24 volts. Do not use any benchtop DC power to plug in to power up an IEPE sensor because you will destroy the accelerometer. This picture here, I like it because accelerometers come in all shapes and sizes. It's amazing to me. We have over 2,000 part numbers at Dytran, and almost every day somebody calls and wants something different. So it's amazing the slight differences that an accelerometer can offer to the application. All right. All right, the next thing I want to talk about is frequency response, the low-end frequency and the upper high-end frequency. Let's first start with the upper frequency. Let's go back to this picture here. It's kind of hard to tell, but this sensor right here, I don't know if you can see my cursor in the middle on the right, is a fairly large accelerometer. This is an industrial accelerometer meant to monitor, rotating pieces of equipment on pumps, motors, things like that. The connector is very, very robust, compared to like the 1032 connector above it. So it's an industrial accelerometer. And so the upper frequency is very limited with that accelerometer because of the size of the accelerometer, the mass of the accelerometer, the connector of that accelerometer makes the upper limited frequency very rough, very difficult to measure. That accelerometer probably has a natural frequency of about 70 kilohertz, but a usable frequency of probably 3 kilohertz maximum. Versus this sensor way over here, this little teardrop has probably a natural frequency of about 100 kilohertz and a usable frequency over 10 kilohertz. So the upper frequency of an accelerometer is dictated by the design of the sensor, the connector, the mass, the weight. All of that goes into the limitation of the upper frequency of the accelerometer. The low end frequency of the accelerometer is dictated by the factory, and it's called the discharge time constant. I don't know if we talked about that. I'm going to show you a graph of it. So DTC is the low end frequency. We put the DTC, the discharge time constant, on the data sheet of the accelerometer, but then the easiest way to determine what your low end frequency is just to look at the data sheet and look at the specification for frequency. We always give you the low end frequency and the upper frequency, and that would dictate what the discharge time constant is. Okay. And so let's just go ahead and show you what a typical output of an IEPE accelerometer looks like up here in the upper graph here. So for accelerometers, we try and set the output of the sensor at 0.2 to 0.3% of the natural frequency of that sensor. We want to stay as far away as possible from F sub n, the natural frequency of that sensor. This is the most linear portion of the output, about 0.2 to 0.3. And then we want to understand this roll-off. So the two main things that you need to remember about IEPE sensors is, one, they're constant current powered, and two, they're AC coupled, right? So they could never measure a static measurement. They can't measure static pressure, static force, or static acceleration. They have a bleed off, and this is the bleed off called the discharge time constant, this low end roll off at your low end frequency. So on the data sheet, we usually give you 2 points of data. We usually give you the 5% data point and then the 3 dB point, which looks like it's 1 hertz here on this accelerometer. Normally, the 5% data point is down here at, say, 1 hertz or 2 hertz. This is not typical of an accelerometer, this graph here, where they're showing it 5% at 7 hertz. That's not typical. Usually it's 1 hertz. All right, but it's important to understand this low end roll off of the accelerometer. And then the other important part of this picture here is the schematic. This is the IEPE schematic that was invented by Kistler in 1978, and now today everybody copies it. Literally everybody. So this is the name. This amplifier right here is the name of IEPE or ICP or piezotron or isotron or CCLD. This is what it is. Okay. I'll come back to that in a little bit. Now I want to talk a little bit about what's inside of these accelerometers. These are two breakout pictures of a shear mode and a compression mode accelerometer. So in the early days of accelerometers, everybody developed their accelerometers in a compression mode. It was the easiest and most cost-effective way to get started making accelerometers. So Kistler and Defco, Dytran, PCB, we all started out with compression designs. And then at some point, we all shifted over to the shear mode design. And today, 90% of our accelerometers, probably like everybody else, is a shear mode design. All right. And we still manufacture some sensors in a compression design, like our shock sensors and our industrial accelerometers. They're very, very robust. But let me just highlight some of the parts in here. Hopefully you can see my mouse my cursor moving around the screen here. But on the left here, on the compression design, this big, let's start on the bottom. The bottom is the base, and at Dytran, we always use titanium as our base for strength to weight ratio. So we have a titanium base, we have a stack of crystals. Looks like we have 4 crystals on this accelerometer that are stacked together, and then we sum that output of those 4 crystals. And then this big silver thing on top is actually kind of green, but it doesn't show it there in the picture. But this thing is called the seismic mass, and this is made out of tungsten. And then we preload the entire stack together with this screw. Okay, so F equals ma. I can get more acceleration output if I put more mass on here, or I can put less and more crystals on here to get less or more output, more sensitivity from the accelerometer. All right. The problem with this design is if the temperature is rapidly changing, this screw is metal. And if I dunk this sensor in ice water, that screw is going to contract and it's going to squeeze this crystal stack. And if you're looking at it on an output of an O-scope, the sensor looks like it's got full scale output with no vibration. And so that problem is called thermal transient response, and it's a very poor part of this design. The other issue is if I have any strain going on in the base of this accelerometer, that strain is going to be right in contact with the crystal, and it's given me an output error because of the strain, whether that strain is from a mechanical stress or it's from temperature changing. Whatever that strain is, it's going to go right into the crystal. And that's called base strain sensitivity. So that's why we don't use the compression design as much anymore. We use the shear mode design. So you can see over here, we still have the base. Here's our titanium, Here's our titanium base. Here's our crystal is right here and right here. And you can see it better right here. Here's the crystal. Here's the seismic mass. We've split it into 2 here and here. But the two big changes that we made is we've decoupled the base from the crystal, so we don't have that base strain sensitivity problem. And then we've developed this crystal and polarized this crystal to only give an output when we see a shear mode, a shear force against the face of this mass. Where this one is being squeezed in compression, this one is being shaken up and down in a shear force. All right. So if I dunk it in ice water, this screw is going to shrink and it's going to compress the crystal, but it's not going to shear the face of that crystal. So that's why we use shear mode today for most accelerometers. And I do have customers that will call and ask for a shear mode accelerometer. That's actually pretty common. So that's what that means. The crystals come in all shapes and sizes, depending on the application, the sensor, etc. But over here on the left is what a piezoelectric crystal looks like once it's been cut and then polarized and then cut again for mounting into the accelerometer, depending on what size. That's what they look like. This is a good cartoonish depiction of what's happening with a piezoelectric IEPE shear mode accelerometer. On the left is what's happening when we're at rest. So we have the crystals, 2 crystals in between an insulator. And at rest, we align the crystals so that their polarity is neutral. So the plus and minus align to give us a neutral output at rest. And then as we start to vibrate or shake the accelerometer, we start to get a deformation and we start to shear the face of that crystal. And we start aligning the sensitivity so that we get a plus in the up direction and a negative in the down direction. All right, so that's kind of what's happening when you're shaking an accelerometer. This deformation that you see right here is actually in the angstroms. The naked eye can't actually see that deformation. All right, next thing I want to do is talk a little bit about noise. I'm going to skip this screen. There's too many words here. I'm going to skip this screen as well and go right to this video. This is a really good video to talk about making sure that you have the proper cable with the accelerometer that you're purchasing. So in the Dytran world, we have white cables are IEPE voltage mode cables. Red cables are low noise charge mode cables. So in this video, I have a charge mode accelerometer with a white IEPE cable. It's the wrong cable, and you're going to see what's happening. I'm not going to vibrate the accelerometer. I'm just going to shake the cable, and you can see what's happening as I shake the cable. We're getting this massive output. What's happening is dissimilar materials are rubbing against each other, building up spurious charge, and that charge has nowhere to go except your data acquisition system. So it looks like an output when it's just noise. So two things wrong with this picture. One, I'm using the wrong cable with a charge mode accelerometer, and I'm whipping my cable instead of tying down my cable all the way off my test article. So if I switch the cable to a red low noise charge mode cable and I start whipping the cable, you'll see that that noise is now dissipated because this cable is wrapped specially to dissipate any spurious charge that's being built up. But you do see a little perturbation there, and that's because I'm whipping the cable and you can't see it, but it's adding a strain to the base of my accelerometer. So two things to remember from this video. One, always get the right cable with the accelerometer that you're buying, and we're happy to help you with that. And then number two, make sure you tie your cables down all the way off the test article. All right. I apologize. I am speaking quickly because I know I only have a couple minutes left. But if anybody has any questions on any of these things, let us know in the chat, or send me an email. I'm happy to answer any questions. Very quickly on this, there's a couple important documents that that you need to be aware of when you're reviewing or researching what accelerometer to use, and then when you buy an accelerometer, what documentation comes with your sensor. So the top document up here is called our outline installation drawing. It's got the dimensions of the accelerometer, as well as, very importantly, how to mount the accelerometer. What is the recommended torque if you're going to stud mount it? What's the recommended surface finish if you're going to glue it down? And so a very important document. We also can offer you, these are all on the website, or we can email them to you. We also have step files, 3D step files for every accelerometer if you need them. The next document is the important data sheet or the specification sheet. So all the pertinent information of that accelerometer, the G range, the temperature, the frequency, the noise, whether it's isolated or not, whether it's got a connector or a cable, all of the pertinent specifications are on here. And then we also give you some typical data points. We give you a low end frequency roll off. We give you a typical phase graph. And then we also give you a typical temperature deviation over the temperature of the accelerometer. So those three plots are on the data sheet. And then the last sheet here is our calibration certificate that comes with every accelerometer. We usually start at 20 hertz and go up to 10 kilohertz. And then we give you 10 points of data, and then we plot those 10 points down here for the response amplitude curve for frequency. We can go down to 1 hertz if you need it. You just need to let us know, and we can go up to 17 kilohertz. We are accredited from ISO from 1 hertz to 10 kilohertz for calibrating accelerometers. Okay. And just a reminder, the calibration data point that you'll see on your box, on the accelerometer box, the sticker, is the 100 hertz data point. That's the reference sensitivity that every accelerometer company uses, 100 hertz. All right. I'm going to skip this. This is TEDS. This is, like I mentioned, the transducer electronic data sheet. We can put your calibration certificate inside the accelerometer, and that's called a TEDS chip. It's a very inexpensive option. And then lastly, just want to wrap up. There's three ways to mount an accelerometer. You can stud mount it, you can glue it, or you can use a magnet. And most customers do use some kind of an accessory to mount the accelerometer, whether you're stud mounting it or using glue. Most customers would prefer to use a base or a bolt adapter so that you don't break the accelerometer if you're putting it on and taking it off multiple times. You would rather break an adapter or an accessory. It's much cheaper. And we have at Dytran, we have hundreds and hundreds of different adapters and accessories that you can use to mount and use accelerometers. The big difference between stud mounting and gluing or using a magnet is the frequency response. By stud mounting the accelerometer, you can get as close to the natural frequency as possible. You can easily get 10 kilohertz output. And then gluing an accelerometer, many customers use glue because they can't stud mount on their test article. By gluing an accelerometer, though, you do introduce a new spring mass system into the measurement, and this can reduce your frequency here. Some customers can get out to 10 kilohertz if you're very good at it. Some have a reduced frequency because they've used too much adhesive and it reduces your frequency. So that's kind of an art, mounting an accelerometer properly with glue to get high frequency. And then lastly, the magnet usually gives us about 3 kilohertz of data. Okay. It's important to make sure that you clean your test article very properly. You blow all the contaminants off with shop air, and then you tie all your cables down off the test article so that you don't get that noise perturbation that we were looking at. All right, I'm going to skip some of this. I can send this email and this presentation out to people that are interested. And then again, as I mentioned, we have hundreds and hundreds of different bases, blocks, bolts, magnets, anything that you ever need to mount and use an accelerometer. All right. We also offer wax. Wax is pretty good. It can get you out to 10 kilohertz, but it is limited in temperature, of course. Here's a great picture of just some of the different accessories that we offer for mounting accelerometers. And then our last slide is do's and don'ts. Make sure you do not drop your accelerometer on concrete. It's okay to drop it on carpet, just don't drop it on concrete. Make sure you calibrate your accelerometers once a year is our recommendation. Make sure you use a proper tool to remove and clean the sensors. Use acetone to clean the sensors. And then just remember that these are a little bit ESD sensitive, so make sure you discharge yourself before using the sensors. They are shipped in ESD protected bags, and if it's an IEPE accelerometer, it's pretty well protected. You just don't want to touch the pin of the accelerometer. But charge mode accelerometers are definitely more susceptible because there's no amplifier inside. All right, and then I have a bunch of other presentations if anyone's ever interested in it. I have a DC MEMS presentation, a high temperature one, smart accelerometers, digital smart accelerometers, and then as I mentioned earlier, how to select proper cables. If you need any of these, I'm happy to send those as well. I was trying to keep it to 1 hour, so thank you for your time. Very excited to be a part of this presentation with you guys. If you have any questions, let us know, and thank you for your time.
Thank you, Kevin, for presentation. And I think we have 2 questions. And one of them is on the chat. It's about charge mode sensors. Is 1200 Fahrenheit temperature continuous?
Yes, we have a sensor called the 3335C. Ali could send you a data sheet on it that is 650C rated continuous. In fact, you could probably take it with excursions of a couple minutes up to 700C. Yeah, 3335C.
Okay, so we have another question in Q&A section. And Mr. Emin Özda, I think. Özdemir, yeah. He asked that he is working on a project about wearable piezoelectric sensors for in-cockpit monitoring. And which piezoelectric materials would you recommend for energy harvesting in wearable and flexible systems used inside an aircraft cockpit? Is it possible to generate usable electrical energy from pressure difference between the cockpit interior and the outside environment during flight?
Yeah, great question. Appreciate that. Maybe Ali and myself and you can take this offline. I would get in, I could get engineering involved, but currently, in my 20 years at Dytran, we've never utilized energy harvesting to power up accelerometers or using wearable piezoelectric sensors. So I'm not very familiar with wearable applications. We obviously utilize a lot of accelerometers in the cockpit, but they're just typical IEPE accelerometers that go to a data acquisition system. Um, like a Siemens data acquisition system. That's very common. We do that all the time with aircraft manufacturers. But I don't have energy harvesting wearable sensors, unfortunately. Sorry.
Okay. I think
But we could
we,
take that offline. So if somebody could send me an
yeah,
email, I could get engineering involved.
yeah.
Yeah.
If you have any questions, you can always send us an email. We have good technical team in the
Yes.
background, and we always happy to help you about your questions. And we also have an accredited calibration laboratory in Turkey. Uh, and if you have any needs or any questions about calibrations of your sensors, we we are happy to help you in calibration as well. Okay, thank you, Kevin. Glad to have you here, and thank you for all of the attendees. And
Thank you.
yeah,
Appreciate it. Thanks everybody for attending. That was great.
we will upload this recording to YouTube in a few days, and you can check out in our channel. Goodbye. Thank you.
Awesome. Thanks everybody. Cheers. See ya.